Our first question today focuses on causal masking. What is the purpose of causal masking in decoder-only transformers? Your options are A. To prevent overfitting, B. To reduce computational cost, C. To ensure autoregressive generation, or D. To improve attention patterns. The correct answer is C. To ensure autoregressive generation. We choose this answer because causal masking is specifically designed to prevent the model from seeing future tokens during training, which is essential for teaching the model to predict the next word based only on previous context. Causal masking is a technique that prevents the model from cheating by looking at future tokens when predicting the next word. It's like reading a book with a piece of paper covering all the words you haven't read yet. You can only see the current and previous words, never future ones. This forces the model to predict each word based only on what came before, enabling true autoregressive language modeling. In simple terms, causal masking creates fair prediction rules. The layman explanation shows us this works like taking a test where you can't peek at the answer key. When generating the cat sat on the blank, the model can only see the cat sat on the but never the answer mat that comes next. This makes the model learn genuine prediction rather than memorization. This teaches honest word prediction. The memory tip reminds us that causal equals cause and effect. Only past causes, which are words, can influence future effects, which are predictions. Remember, past influences future. Our next question explores the attention mechanism. In the attention mechanism, what determines which values are retrieved? Your choices are A. The similarity between keys and queries, B. The magnitude of the values, C. The position in the sequence, or D. Random sampling. The answer is A. The similarity between keys and queries. This is correct because the attention mechanism works by computing similarity scores between what you're looking for, the query, and what's available, the keys, to determine which information, the values, should be retrieved. The key query value mechanism works like a sophisticated library system. The query is your question, such as, I need information about cats. Keys are like book titles or topics such as animals, pets, mammals, and values are the actual content. The system compares your query with all keys to find the most relevant matches, then retrieves those values. The similarity score between query and key determines how much attention each value receives. This creates a smart information retrieval system. Picture asking a librarian for information about flying animals. The librarian checks all book categories. Birds equals 95% match. Insects equals 80% match. Fish equals 10% match. Based on these similarity scores, you get mostly content about birds and some about insects, weighted by their relevance scores. Smart matching finds relevant information. The memory tip teaches us that question finds the right key to unlock the value, like a treasure hunt. Think, treasure hunt for information. Our next question addresses a crucial architectural component. What problem do residual connections primarily solve in deep networks? The options are A. Overfitting, B. Vanishing gradients, C. Memory usage, or D. Computational complexity. The correct answer is B. Vanishing gradients. We select this because residual connections specifically address the problem where learning signals become too weak to reach early layers in very deep networks, which is the classic vanishing gradient problem. Residual connections are like express highways in a complex city road network. They create direct shortcuts that allow information to flow directly from earlier layers to later layers, bypassing the normal processing route. This prevents the vanishing gradient problem where learning signals become too weak to reach the early layers in very deep networks, like whispers getting lost in a long chain of people. These create information express lanes. Imagine a 50-story building where messages must be passed floor by floor. Without elevators, which represent residual connections, a message from floor 1 might become garbled by floor 50. Residual connections are like express elevators that ensure the original message, plus any improvements from each floor, reaches the top clearly. For example, input x equals 5, after processing f of x equals 3. With residual, the output equals x plus f of x equals 5 plus 3 equals 8. Express elevators preserve original messages. The memory tip tells us that residual means leftover, We keep the original input as leftover and add the new learning to it. Keep originals, add improvements. Our next question examines the mathematical foundations of attention. Why is the dot product scaled by the square root of the dimension in attention? Your options are A. To prevent numerical overflow, B. To normalize the variance, C. To reduce computational cost, or D. To improve convergence. The answer is B. To normalize the variance. This is correct because as vector dimensions increase, the products naturally become larger, and scaling by the square root of the dimension keeps the variance controlled, preventing the softmax function from becoming too extreme. Scaled dot product attention is like adjusting the volume on a stereo system to prevent distortion. When we multiply two vectors using dot product, the result grows larger as the vector dimensions increase. The scaling factor, 1 over square root of d, acts like an automatic volume control, keeping the attention scores in a reasonable range so the softmax function doesn't become too extreme, meaning all attention on one item versus balanced attention. This provides automatic volume control for attention. Without scaling, query.key might give scores like 1000, 2000, 1500. After softmax, this becomes 0.001, 0.997, 0.002. Too extreme. With scaling by square root of 512, approximately 22.6, we get 44, 88, 66. After softmax, 0.2, 0.6, 0.2. Much more balanced attention distribution. It's like adjusting microphone sensitivity in a noisy room. Scaling creates balanced attention distribution. The memory tip reminds us that scale equals balance. Just like balancing ingredients in cooking, too much of one thing ruins the dish. Balance ingredients. Balance attention. Our final question covers the architectural structure. How many transformer blocks does GPT-2 Large have? The choices are A. 12, B. 24, C. 36, or D. 48. The correct answer is B. 24 transformer blocks. This is the specific architecture of GPT-2 Large, which uses 24 stacked transformer blocks to create its processing depth. A transformer block is like a complete processing unit in a factory assembly line. Each block contains, first, multi-head self-attention, which is the focus component. Second, layer normalization, which provides quality control. Third, feed-forward network, which is the thinking component. And fourth, residual connections, which are the express lanes. These components work together to process and refine information, with each block adding another layer of understanding to the model. Each block creates a complete processing unit. Think of GPT-2 Large as a 24-story office building where each floor, representing a transformer block, has a conference room for team discussions, which is multi-head attention, a supervisor ensuring quality, which is layer norm, individual offices for deep thinking, which is feed-forward, and express elevators, which are residuals. Each floor processes the work from below and passes improved results upward. 24 floors of intelligent processing. The memory tip teaches us that transformer block equals attention plus normalize plus think plus skip connection. Like ANTS building intelligence. Remember, ANTS build intelligence.